Ladies and gentlemen, the presentation this evening is by Emeritus Professor Laurie Doctors. Laurie obtained his bachelor's and master's degrees from the University of Sydney and then his doctorate from the University of Michigan in the USA, and commenced teaching naval architecture and researching hydrodynamics at the University of New South Wales, now UNSW Sydney, in 1971. And as a matter of interest, I was in Laurie's first ship hydrodynamics class. During his career, most of Professor Doctor's research efforts have been devoted to numerical ship hydrodynamics, where his interests have centred on the study of advanced marine vehicles. These include monohulls, catamarans, multi-hulls, air-cushioned vehicles, surface effect ships, planing boats, wing and ground effect craft, and hydrofoil boats. He has spent periods of research and sabbatical leave at the David W. Taylor Naval Ship Research and Development Centre, Tel Aviv University, the University of Michigan, the Australian Maritime College, and the University of Strathclyde. His research has been sponsored principally by the Australian Research Council and the US Office of Naval Research. In January 2018, Professor Doctors published the second edition of his comprehensive 2-volume, 20-chapter book, Hydrodynamics of High-Performance Marine Vessels, which describes the behaviour of all types of seagoing craft. He is continuing his research as Professor Emeritus at UNSW Sydney. Ladies and gentlemen, I'll pass you over to Laurie Doctors.
Well, first of all, Phil, thank you very much for inviting me to give this presentation some time ago, and your invitation was what spurred me to do a little bit more work on this subject. So I'm grateful for your promotion of my work. In addition, I'd like to thank Vatsal Thakkar from the Institution of Engineers for organising the technical side of the presentation tonight. Before I start my presentation, I should just point out in the middle of the screen, you can see my email address. So if someone would like a copy of my presentation, they should email me and I can send them a copy of the presentation. In addition to that, I'll be writing up the presentation as a paper, and that'll be appearing in the next issue, or the August issue of the Australian Naval Architect. So the topic, as you can see, is the hydrodynamics of the Sydney Harbour RiverCat ferries, and this work actually goes back 3 decades to 1991, or to be more precise, the year before that, when the calculations were done. Everyone in this listening tonight will be aware that there are 7 RiverCats operating along the Parramatta River and into Sydney Harbour. They also sometimes operate in other parts. And here are the topics. As you can see, the 6 topics that I'll talk about tonight. In brief, however, it breaks down into 2 main topics. I'll firstly talk about the resistance of the catamaran, because obviously we're interested in reducing the power required to drive it through the water. However, the main focus of the work at that time was the wave generation. That'll be the second part of the talk. There was a big interest in minimising the generation of the vessel, generation of waves by the vessel, which could damage the banks of the river. I'll first just describe the vessel so you just have a better idea of what it looks like. This picture was taken during the presentation in 1991. You can see someone there holding a camera up, taking a picture of it, and that's the Dawn Fraser, which was one of the first 2 vessels to be built and delivered for operation. You can see it's moving at quite a speed, and there's a very little wave pattern behind it. Here's another picture of it leaving the wharf at Parramatta, and again you can see the picture emphasises the very narrow hulls, which is the secret to the low wave generation of this vessel. Here's a general arrangement of the vessel. The upper part of the slide shows some of the principal dimensions. We can see L, the wetted length of the vessel. We have B, the overall beam. B1 is the beam of the demi-hull, and S is the spacing between the two demi-hulls. Normally the spacing is taken between the center planes of the two demi-hulls. Here you have the principal hydrostatic particulars of the RiverCat. The first line there shows you the length, 35 meters. The demi-hull beam B1 is 1 meter. So the vessel demi-hulls are extremely slender. The length to beam ratio clearly 35:1, which I'm sure is a world record. The overall beam is 10.06 meters. The draft 1.226 meters, and you can see the other coefficients there. The interesting one there is the slenderness ratio, which is 11.68. The slenderness ratio is defined as the length divided by the volume to the 1/3 power. So the vessel is very slender. Another parameter we'll be talking about later in the presentation is the transom ratio. That's to say the area of the mid area, which is slightly under 1.5. The standard space of the vessel is 55 tons with normal load, and the power is provided by two engines of 335 kilowatts each. The nominal operating speed, I use the symbol U there, is 23 knots. This is what the demi-hull looks like in the computer program which I used to do calculations. Front view, split view. So the right side shows you the forward part of the hull, and the left-hand part of this view shows you the stern. So where I'm showing you with the arrow, that's the transom stern. Our view there is
Laurie, you haven't
really
showed there we go, yeah.
I'm having a bit of trouble with the keys don't seem to be driving the screen very well at the moment, Phil, but we'll struggle on. Now, the first part of the presentation is to do with the resistance of the vessel, which was not the main driving force. The vessel, can you hear, Phil?
Yes.
Okay, the assumed components of the resistance are like this. RT is the total resistance, and it's made up of these components. RW is the wave resistance, which is due to the fact that the vessel generates a wave pattern, and obviously you need energy to do that. An additional drag component is the second one, RH, that stands for the hydrostatic drag. Any vessel with a transom stern, as it starts to pick up speed, so the water level drops behind the transom, so you no longer have the hydrostatic pressure acting on the transom, and as a result of that you get an additional drag. Now that sounds like a bad feature in a vessel, to have additional drag from the lack of hydrostatic pressure there. However, it seems to me that the story is more complicated than that. With the transom stern, you generate a hollow behind the vessel. That means the effective wave-making length of the vessel has been increased. So the first term, the wave resistance, is actually reduced to some degree. So it's not actually obvious, without doing the calculations or without doing experiments, whether the presence of a transom is a good thing or a bad thing from the point of view of resistance. The major component of the resistance for this vessel and indeed for many waterborne vessels is the frictional resistance, RF. This can be calculated by a number of formulas, and in particular the 1957 ITTC formula, International Tone Tank Conference, is often used. You'll get a slightly different result if you use a different formula. In addition to that, it's traditional in naval architecture to multiply this calculated figure RF by a form factor which accounts for the shape of the hull, and that's a completely new discussion. In addition to that, the model ship, of course, is when tested in the towing tank, is considered to be hydraulically smooth, so it's got no roughness whatsoever. When considering the full-size vessel, you have to make an allowance for some natural roughness in the hull, or even some growth of fouling on the hull. So the symbol I have for that is RA. That's the A stands for allowance. That's the allowance in projecting the resistance from the model to the full-size vessel. And another term that people often consider these days is RA. This is lowercase a, the aerodynamic drag. However, my experience is the aerodynamic drag is very, very minimal for almost any vessel that we're interested in. Now, if you're interested in the calculations, how I developed the formula for the resistance of the vessel, you can look in my book. It's a fairly complicated analysis. It assumes that the water is inviscid. It assumes the analysis assumes that the demi-hulls are thin. And as a result of that, it assumes the wave generation is fairly small. And I like to boast every time I mention this, that the initial formula for wave generation was developed by an Australian at the University of Melbourne in 1898. So it does have a long history. However, the formula has been modified over the years to include the finite depth of the water. The initial work was over 100 years ago, assumed the water was deep. The formula also allows for the width of the waterway. And you can see here, I've got the dimensions of the towing tank that we used for these experiments. The width divided by the length of the vessel is about 2.5. And the depth divided by depth of the water divided by the length is 0.1. So this is a very shallow water case. The theory has been expanded further to allow for multi-hull vessels. And in this case, of course, we're talking about 2 demi-hulls. And it's important to note that the 2 demi-hulls, they each produce their own wave pattern as if they were a monohull. However, the wave system from each demi-hull encounters the sister demi-hull. As a consequence of that, the wave resistance of the whole catamaran is not simply the sum of the resistance of one hull multiplied by 2. It's a complicated interaction between the two, and all of that is accounted for in the formula. Now, what we have along the bottom is the Freud number based on the length of the vessel. So that's the velocity of the vessel divided by the square root of GL, where G is gravity and L is the length of the vessel. So this is the dimensionless speed. The operational speed, as I mentioned before, is about 23 knots, which corresponds to roughly where I'm showing you with my arrow. It's towards the right side of the graph. Now here we have the components that I talked about before. The orange line is the hydrostatic drag, which is fairly constant over this particular speed range. This is not the entire speed range. We're plotting from 0.4 to 0.5. So over this range, the transom is fully dry, or so the theory says, fully dry, and so consequently the hydrostatic drag is constant over this length. The red line here, the red dashed line, that's the wave resistance. And in this particular case, the maximum wave resistance is somewhere here, but it actually drops off a little bit. So the main hump, as we call it, is at this condition here, a Freud number of about 0.45, and then the wave resistance drops off after that. But the lion's share of the resistance, you can see, is the green line here. This is the frictional resistance. I should point out that all of these components of resistance have been made dimensionless by dividing by the weight of the vessel. So the displacement in tons is 55, and to do things correctly, you have to convert the weight into newtons. If you add up those components, you get this blue line here. Now the next question is, how are we going to improve on that calculation? If we assume the form factor is 1.090, we get the purple line. So the assumption here is that the form factor is 9% more than for a flat plate. And here we have the experimental points. The towing tank work was done at the Australian Maritime College in 1990. You can see the experimental symbols there, the circles, and the rather good agreement. between the theory and the experiment. Now, this is for a very shallow water case. The depth divided by the length is 0.1. We can go to a more interesting case where the depth over the length is 0.2857. And I need to show you that the red line here, which is the wave resistance, it's bigger than it was in the previous diagram, because in this particular case, we pass through what is called the critical speed. This is where the Froude number based on the depth is equal to 1. And according to theory, there is a sudden drop in resistance at this speed. So this happens to be a very interesting case academically, as well as a practical case for the operation of the RiverCat in the river, which is usually the Parramatta River in our case. So there's this, what happens is this sudden drop here results in the, which due to the fact that the transverse wave system drops out at that critical speed. And we'll see a bit more of that in the next slide. There you see the green, the frictional resistance, and the blue line here is when you add all the components together. And if you again use this 1.090 for the form factor, you get the purple line here, which again agrees quite well with the total resistance measurements made in the towing tank. There is this point here which I'm pointing out, and I really don't have much time to talk about that, except to say that the theory here assumes that the wave system is steady state, that the towing tank is infinitely long, and the wave pattern is absolutely steady. Now, in any real towing tank case, this is not the case, that you don't develop this transverse wave system that I mentioned completely, because all towing tanks have got a finite length. And as a result of that, for the condition just below the critical, the experimental measured drag is always a bit less than the steady state theory would tell you. This discontinuity in the resistance curve is given by this unbelievably simple formula that says delta RW over W, the change in wave resistance, made dimensionless against the weight, is 3 times the volume of the vessel, which would be in cubic meters. And then you have to divide by 2WD squared. W is the width of the canal or the towing tank. D is the depth of the water. So you can see if it's shallow water, as the water becomes shallower, this jump effect is greater. And if the width of the waterway or the towing tank is less, again, this jump becomes greater. So that shows you one of those interesting phenomena that we can analyze theoretically. This last graph here, the last of this set of graphs, shows you again the Froude number along the bottom. Along the vertical scale, we have the specific resistance, as it's called, the total resistance divided by the weight. And we've got the 3 depths that that we were interested in. They're indicated up here. The depth over the length of 0.1, the intermediate case, 0.2857, and the deep water case, where the depth was 1.071 times the vessel length. So there are 3 sets of curves there and 3 sets of experiments. And it is very pleasing to see that the theory does order them correctly. If you look at the, if we go from shallow to deep, that's red to green to blue. In this speed range here, the high speed range, the resistance increases by a small amount. That's shown up by the experiments. And it's the reverse at the lower speeds. So the experiment is able to fit in nicely with the theory. I should point out that we have a false 0 here. The scale starts off as 40, and there's a multiplying factor of 10 to the minus 3. So you need to, if you're interested in getting some numbers of this for design purposes, you'd have to read off this scale, so say this number here, 80. You have to divide by 1,000. And then, of course, that is the resistance divided by the weight. So you have to multiply by the weight of the vessel to get the actual resistance in newtons. So that's the resistance of the vessel. Now, an interesting thought would be, can we do better than the original design by making some changes? And I looked at 4 different variations to the basic hull. These are indicated here. I've numbered them 1, 2, 3, and 4. The most obvious one, which I've alluded to already, is to play with the slenderness ratio. So this term here, affine, that's a mathematical term which refers to the fact that you might like to change the shape of the vessel, and you do so by a simple stretching process. So in this case, affine 0 refers to the original hull, the original RiverCat, which is what you see on operating every day now. And we've got a single stretch, affine 1, and affine 2 is an additional stretch of the hull. So we're stretching it from 11.68 to 14.60 to 17.52. That last figure is a 50% stretch. So that is the displacement remains constant at 55 tons. The length is going up from 35 tons to 50% more than that. So the slenderness ratio increases as you go. Now, obviously, if you're stretching the length to make this comparison reasonable, you have to reduce the beam and the draft in proportion in order to keep the displacement constant. In the second process, we're changing the beam to draft ratio, so keeping the length the same and just changing the beam of the being held divided by the draft. This is the original figure here, 0.8159, and we're increasing it up to 1.836. Another transformation that one can consider is leave the demi-hulls the same as they were originally and just increase the spacing between the demi-hulls. This is the original demi-hull spacing, and some experiments were done with a greater spacing, and then I've increased it even further for the calculations. And then the last exercise is the transom area ratio. The original hull, as I pointed out, has a transom area ratio of 4.431, and you can obviously consider a case where the vessel has a pointed stern, in which case the figure will be 0, and then there's the intermediate case where it's half the value. This shows you the demi-hull I created in my computer hull with the computer program with the pointed stern. So the bow section is the same. I haven't changed that. And what I've done is I've replicated the bow section and placed it at the stern. Now, if you simply do that exactly the way I just described it, the displacement of the vessel will be a little bit less than the original, which is what we don't want, because we want to make a fair comparison. So I've increased the beam and the draft slightly in order to maintain the same same displacement of the demi-hull. So far now we have two hulls that we're considering. The original one with a full transom stern. There's this one, which I've called the pointed version. And then there's what I've called the blended version, which is halfway between the two. So my computer program is able to blend two hulls and come up with a compromised version. If you look carefully at the stern, it does have a transom, but this transom is half the transom of the original vessel. So there are those four transformations. So I'll show you 4 slides now showing the effect of the different transformations. And these are all to do with the resistance. And then later on in the second part of the talk, I'll talk about the wave resistance. So here you see the length is changing from 35 meters up to 52.5, and consequently the slenderness ratio is increasing in sympathy with that. We have the volumetric Froude number here. Now, the reason I've chosen the volumetric Froude number there instead of the regular Froude number is because the length is changing, and we really want to compare the performance of the vessel at the same speed. And if you change the length of the vessel, then the Froude number changes, which is really an unintended side effect. With the volumetric Froude number, that's defined in a similar way to the length Froude number, except you don't use the length in the denominator, you use the cube root of the volume. So it's a good way of comparing two different vessels. You can also obviously a catamaran with a monohull and so forth, and it's a fair way of making a comparison, because presumably a vessel with a particular displacement, whether it's a catamaran, monohull, or any other type of marine vehicle, presumably the usefulness of the vessel in terms of carrying cargo or passengers is basically related to the displacement. As you can see, there's not a big difference in changing the length. And what's happening here is that so the three curves refer to the three different lengths. And what's happening here is as you make the vessel longer, so the wave generation is less, the wave resistance is less. Unfortunately, of course, you're increasing the wetted surface. So the frictional resistance increases in sympathy with that. And the two, to a large degree, seem to counterbalance. So there's not a big deal, there's not a big improvement in the performance of the vessel in terms of reducing the drag by making the length greater, except perhaps in this region here. But in the operating condition, the 23 knot case up here, that's indicated by this little purple square, the operating condition is, it makes almost no difference at all. By comparison, I've put another little dot there to show what would happen if you could make the vessel perfectly smooth. If you took the vessel out of the water every single morning, cleaned it of all the fouling and put it back in the water so you'd have no roughness at all, you would actually reduce the resistance by that margin. The next slide shows changing the beam to draft ratio. There is a slight improvement in increasing the beam to draft ratio of the demi-hull. You can see going from the original red line down to the blue line. And the reason for that is that the sections of the demi-hull are becoming more circular, or semicircular to be precise. The semicircular cross-section gives you the least wetted surface and hence the least frictional drag. And frictional drag is a big component of the drag. So the total drag. So if you're interested in reducing the total drag of the vessel, you'd like to reduce the frictional resistance, and that means one should aim for semicircular cross sections. Here we're changing the demi-hull separation, and there's very little advantage in increasing the demi-hull separation. If you look carefully at the graph, if you go from the red line to the green line, that's where you're increasing the separation between the demi-hulls, and that does reduce the wave resistance, but very, very small amount. So that's not really a big practical gain there. Here we're playing with the transom area, and as you go to a lesser transom area, the red line, remember, is the original one, the dashed red line is the original vessel. As you reduce the prominence of the transom stern by going to a blended stern or a pointed one, you do reduce the resistance, but not very much in this case. Hull finish, I'm going to skip over this because time is beginning to run out. I'll just mention something called the transport factor, which is defined as the weight of the vessel times the speed divided by the required power. This is a measure used to define the effectiveness of any kind of vessel, aircraft, marine vessel, even a motor car. And one aims for a high transport factor. This is very important when we're trying to reduce pollution, because if the vessel has a high transport factor, that means the engine is smaller and you're consuming less fuel. Let's finish my talk by talking about the wave generation. The experiments were done like this in the towing tank. The blue line at the top and the blue line at the bottom represent the sides of the towing tank, and running down the center plane of the towing tank, you've got the two hulls there, and you can see the critical dimensions. You have L, the length of the hulls. You have B, the overall beam. B1 is the beam of one demi-hull. S is the spacing between the two demi-hulls. The vessel will generate a wave pattern, and typically we like to talk about the angle of the bow wave system here. In my notation, I use the symbol θ2. This is the Froude angle, Kelvin angle. Kelvin was the first person to develop the theory for the angle of the wave system, and that's known to be about 19.5 degrees. But that result is only true in deep water, and it's stated 19.5 degrees for all different Froude numbers. However, in shallow water, It varies with the speed and it depends on the depth of the water. And that's a more complicated thing. Again, you could read more about that in my book. The probes, wave height probes, were arranged like that across the width of the towing tank. The wave probes consist of a single wire, and the system, the electronic system, effectively measures the electrical resistance between the wire and the water. So as the wave height varies, so you get different electrical resistance of the wire, and that gets transformed into the wave height, or wave elevation, I should say. Now the vessel, these wave probes are fixed in the tank, and the vessel moves by, so you effectively get a figure like this. Now we'll look at the upper figure first. So this is the start of the wave pattern, and these are the cutoff points. So we're analysing between x1 and x2. X is the longitudinal dimension, and zeta is the wave elevation. So we expect a wave system that looks like this. It starts off from 0 ahead of the vessel. And this will all be at one particular offset from the track of the vessel. So you get a bow wave like this, and then as you go downstairs, it's downstream. So the wave generation, wave elevation drops off. However, you're doing these experiments in a towing tank, so at some point sufficiently far downstream, you'll get a reflected wave off the tank wall, which is something we do not want. So we would like to do the analysis, making sure that we don't go too far downstream. H there is the definition of the wave height, so it's the maximum difference between a peak and a hollow. There are some difficulties with this, which we were discussing at the time of the original work in 1990. You could get away, this is unlikely, it's not likely, but it is possible. It's possible either in the experiments, and it's possible in the computer program that simulates the work. You could get a wave shape like that, in which case this definition of capital H really breaks down, because the maximum difference would, in this case, be from there to there, whereas obviously we really would want the difference between there and there. So that's something that's up for discussion. Here are some experiments done in the shallow water case that we referred to before, depth divided by length 0.1. And this is not at all an unrealistic depth, because 0.1 would mean the depth of the water is 3.5 meters. And in fact, the depth of the Parramatta River is less than that at its head. So this is not at all an unrealistic shallow water value. Along the bottom, we've got the volumetric Froude number here. And on the vertical scale, I've made the height of the wave dimensions using the volume to the 1/3. I know this is an unusual way of doing things. Traditionally, if you're going to make this dimensionless, you divide H by the length of the vessel. But as I said already, we are going to look at some variations where we increase the length of the vessel. And so you want to make a fair comparison. And this fair comparison has to be done with the same Froude number based on the volume. And it also has to, when you finally do the comparison, you have to make the measurements, only the wave height, dimensionless with respect to something that's not changing. In this case, it's the volume. We can't do it with respect to the length because that is changing. So we have 5 sets of results because we had 5 wave probes at these different offsets from the track of the vessel. They're indicated by these symbols. The blue dashed line is the mean of the 5. In the original work that was done in the towing tank, it was decided that a simple measure of the wave generation characteristics of the RiverCat would be the average of these 5 values measured at these 5 different offsets. You can see the largest offset is at 65% of the vessel length. The black line represents the theoretical calculation. Again, you can read about that in the book. There's more detail there. The calculation of the wave system to produce this curve is much more involved than the calculation of the wave resistance. It involves much more work to get the actual wave pattern. But you can see there's a fair agreement between the theory and the experiments. The interesting thing is that as the speed increases, in this particular case, we're talking about the depth over length of 0.1. As you increase the speed, basically the wave height drops off. The next case is the most interesting one of all. Depth over length is 0.2857. That's the intermediate depth that we looked at already. So we've got a fair amount of data here on this graph, which requires explanation. Along the base, along the abscissa, we have the volumetric Froude number. And again, if you want to bring this into real terms, for the RiverCat, 23 knots corresponds to about 1.9 on this scale. So these are the practical values when the vessel is operating at the nominal operating speed. The ordinate is, again, the wave height. That's this maximum difference between crest and trough, made dimensionless against the volume of the vessel to the 1/3. So you will remember that with the wave resistance, that the wave resistance suffers this jump at the critical case when the depth Froude number is 1. And so we see a similar interesting phenomenon with the wave elevation. The symbols are the experiments, and you can see the experiments are indicating a high wave resistance, and then it drops off afterwards. And the theory is the solid line, which you can see here, and then it continues here. The fascinating thing about this is that the theory, in fact, misbehaves even more so for the wave elevation than for the wave resistance. In fact, this curve goes to infinity. And this all boils down to the fact that the theory is steady state theory. It assumes the towing tank length is infinite and assumes that the runners taking is over a long distance in the tank, which is never the case. I should add that if someone is interested in the unsteady theory, which properly accounts for all of these strange phenomena, that can be done as well, and I've got references on that. I've got also here the dotted line because there's a very interesting formula for the wave elevation when you get close to the critical condition. This is the amplitude of the transom wave, and you remember there was a very simple formula for the jump in the wave resistance at the critical condition. Well, there's a very simple formula for the wave elevation, and this wave elevation refers to the transverse wave. It's the transverse wave which causes us this trouble. Once again, you can see in the denominator the width, so the width of the tank. If you increase the width of the tank, this phenomenon will be reduced. If you increase the depth of the water in the tank, the phenomenon will be increased. But what is really striking, to the largest degree, is the shape of the vessel doesn't come into the calculation. The only way the vessel comes into calculation is here through the volume, measured in cubic meters in SI units. Unbelievably, that when you're close to the critical condition, when the depth Froude number is close to 1, and we're talking about just below a depth Froude number of 1, the amplitude of the transverse wave depends only on the entire volume of the vessel and not on its shape. You can see that if FD is equal to 1, then this formula goes to infinity, which is what I was saying before. So that's a steady state result, which we're not getting in a practical experiment tank. And here I've made it dimensionless. And that produces the dotted line I showed in the previous graph. So there's actually a very simple approximation to the height of the wave system in that condition. This is the deep water case, where the depth over the length is 1.071. And there's a fair agreement now between the theory, which is black line, and the dashed line, which is the average of the experiments. And here are all three sets of results together. So the theory is able to differentiate the three cases of the water depth. So in this case, the shallowest water gives you the lowest. I'm now talking about the high speed range. The shallowest water gives you the lowest wave generation, and the deepest water gives you the greatest wave generation. And the ordering of these results with respect to depth is the same for theory and experiment, which is a pleasing result. My screen is just jammed up. Okay, we can do the transformations, and we're slowly coming to the end of my presentation. We can do the those 4 transformations that I did for the resistance. Now these calculations have been done here for the model. You can see the model displacement, and since the model will replicate the full-size vessel for wave generation, it does not do so for resistance, because as we all know, the Reynolds number is much smaller for a towing tank model. So the model resistance is always higher than the full-scale resistance on a dimensional basis. So when one goes, as we know, we model scale to scale. When we do the extrapolation, the total resistance has to be corrected for by the standard Froude method. That process is not required for wave generation, because according to the assumption, the wave generation is the same for model and full scale, since we're making the same assumptions. Here you see the original RiverCat here. This is the symbols. That's the original RiverCat. Model length was 1.4 meters. It's the original data on the towing tank. This is the dashed line. This is the theory, which is replicated fairly well. Now, we obviously didn't do the experiments. I would like to do the experiments, and if someone would like to volunteer, I'd be happy to be involved in that project. This is the theoretical part of my presentation. If we increase the length of the vessel as much as 50%, going from 1.4 meters to 2.1, you can see there's a dramatic reduction in the wave generation. In fact, in this particular speed range here, the wave generation is reduced to less than half. This is the deep water case, I must emphasize. The results will be different for different depths of water. This is where we're changing the beam to draft ratio. Almost no, if the 3 curves represent the 3 different variations of beam to draft ratio, and almost no change there. So that's not a useful exercise. Here we're increasing the demi-hull separation. Now, we did have 2 sets of model tests. We had the finalized results for the RiverCat, and this case here with a greater S over L, that's the greater spacing, that's an extra 1 meter, sorry, extra 2 meters to the spacing. And you can see that the experiments go from the red dots to the green ones, and you do get a reduction in wave generation when you do that. So increasing the spacing between the demi-hulls of a catamaran is a good thing for reducing the wave generation. And if you increase the demi-hull separation further, so then we'll get an even greater reduction in wave generation. But the amount is not enormous, and so I assume that there are practical considerations which would suggest you don't do that. And here we're playing with the transom area, and there is some effect at the lower speeds, but at the higher speeds, not a great effect. Okay, the very last part of my presentation will be the monohull version, because one can ask the question, why not go for a simple monohull instead of a catamaran? So I've generated a monohull from the body lines of the RiverCat by the simple expedient of increasing the beam and the draft by the square root of 2. So we've now got one hull, but the same displaced volume. So we can fairly compare the monohull with the catamaran. The red line is the catamaran, the RiverCat, and you can see when we go to the monohull that the wave generation becomes substantially greater. So this is a very strong recommendation for the catamaran design that was chosen. This is at a water depth of 0.1. This is the critical case where the depth over length is 0.2857. Not much of a difference at low speeds, but high speeds, and in particular, when we're considering 23 knots, you're much better off with the catamaran than the monohull. The wave generation is a lot less. And the next curve is the deep water case. Depth over length is 1.071. And again, if you look at the operational case, the wave generation is substantially higher for the monohull. So we've made a very strong case there for the catamaran. So these are the conclusions. I know time is running out. The conclusions are that the RiverCat is a very, very good design in terms of the resistance and generation. You can improve on it by making the length of the hulls longer, greater, but of course I'm sure that will cause some concern because the longer vessel will be more difficult to maneuver. So the question is, how important is the environment to us? So if we're prepared to put up with a longer vessel, which I suspect is going to be structurally a bit more of a concern, we could actually reduce the wave generation even more. I'll finish with one last comment. I was told, and I remember I was told, this is now 30 years ago, I was told that there was some thought of making the vessel longer. And the way I remember the explanation is that if this vessel were 1 millimeter longer, so it was 35 meters plus 1 millimeter, it would have required an extra crew member because the manning requirements would have changed. And that, of course, would have made the vessel far less economic. So there are other matters to be considered as well as hydrodynamics when considering the design of catamarans or monohulls. So there's question time, and that's the official slide from Institution of Engineers. Phil, did you want to?
Yes, okay. Well, thank you, Laurie, for your presentation. We have a couple of questions there, and the first one is from Ming-Jae Bai. He says, I'm wondering, is it possible to find out more information about lorry doctors, such as on LinkedIn? Do you have a LinkedIn profile, Laurie?
No, I do not have a LinkedIn profile.
Okay, well,
if he wants to send me an email, I will send him my CV.
Okay. The other possibility is for him to search for lorry doctors on the net, and he will find hundreds of publications.
Yes, if you type in doctors space hydrodynamics, you'll get quite a few results.
Sure. The next one is from Jacques Callord, and he says, while the information on the surface wave was very interesting, are you going to cover what appears to be a deep water surge that hits the banks?
Yes, well, at the time, I'm going back almost 30 years, people were often talking about a pressure wave. You've just used the term surge, but I think what we're talking about here is the transverse wave. And unfortunately, we have to live in the real world where there are laws of physics which we're not able to manipulate too much. And unfortunately, according to the theory, the wave elevation becomes infinite. That's the steady state case. That never actually happens in practice. In practice, there are unsteady effects, and I've written some papers on the unsteady resistance of a model in the towing tank. And I've also written papers on the unsteady wave generation. And I think that's what we're talking about here. And you can get very good agreement if you use the unsteady wave resistance theory. You get very good agreement with the experiment. But again, if someone wants to email me with the request, I can send them the relevant papers.
Okay, thanks, Laurie. The next one is from Michael Davis, and he says, is riverbank damage just a function of wave height, or does it also depend on the rapidity of wave height change?
Well, that's the most difficult question to answer. It's easy to answer that question, actually, by saying I don't know. There was a thought. I do have some thoughts on it, however, but I have not done any research on it. Here are the thoughts. First is the frequency of the wave. So you might say, well, can we change the frequency of the wave? And there was a person from industry who came to me. He was interested in the RiverCat, and he was interested in doing some work on it. And he asked me the question, He says, he said to me, okay, we know there's a problem with the wave height. If we change the design of the vessel so that the frequency of the wave is different, will that improve matters? So I thought that was an excellent thought. I went back to my desk and pulled out the equations. Rather sadly, the frequency of the waves, which is intimately connected with the wave length, it depends only on the speed of the vessel. So unfortunately, we're once again stuck with the basic laws of physics. There's nothing you can do to change the frequency of the wave system, unfortunately. Another thought I had on this matter was, do you really want to minimize the wave height? It has occurred to me that you might actually find a vessel that produces a higher wave might be less damaging than one that produces a smaller wave, because the smaller wave might work its way all the way to the banks, where it might erode the banks. The higher wave might actually break as it approaches the banks where the water is shallower. The wave might actually break before it reaches the bank. So there's actually an argument there that maybe a higher wave might actually be better because it crashes before it or spills over before it reaches the bank. But I don't know what the exact answer to that is. It's only a thought.
Okay,
So I've only
thanks.
given a couple of thoughts, but the question is a very difficult one. If you're asking about erosion, it's a much more difficult problem than the work that I've been doing, which is
Okay, thanks. The next one's from Nigel Hay Smith, who says, "Hi, Laurie, great talk. Wondering where we can find your book."
Oh, well, if he emails me, I'll send him the link, but I think the link is on the internet, but I can send him the link.
If you look for Laurie Doctor's Hydrodynamics of high performance marine vessels, you'll actually find it on Amazon. The next one is from...
While on that matter, now you've raised that matter, I should make a point here. If that link doesn't, there might possibly be a problem with it. I haven't checked it lately. There was a fight between Amazon.com and the Australian government about 3 years ago, I think, because the Australian government, I think, was requiring Amazon.com to collect sales tax of some sort. And what happened was Amazon.com told the Australian government something quite rude, which I can't say on the computer here. And I think it became impossible to buy my book for the time being. So if that doesn't work, I'd like the person to let me know and I'll see what I can do about it. But there was a problem with getting the book in Australia because there was a fight between Amazon.com and the Australian Taxation Office.
Oh, fortunately, I got my copy before all of that happened, Laurie.
Yes.
The next one is from Aidan Stanger. He says, "Is it possible to enable it to operate in shallower water without significantly impacting its performance elsewhere?"
No, I'm not quite sure what that means. You mean redesign it for shallow water?
Not sure, it doesn't say.
Yes, well, I can give an approximate answer anyway. My feeling is, calculations, is that the slenderer the vessel, the better, no matter what the depth of the water. So if you're designing it for, if you feel you're doing something special to make it better in shallow water, I'm almost certain it'll be better for deeper water as well.
Right, okay. Thank you, Laurie. The next one's from Robin Sandell. Hi, Robin. He says, "Have you examined the 10 new RiverCats that will soon go into service on the Parramatta River? If so, what do you think of their resistance and wave generation properties?"
I don't have any information on them, so I don't know.
Very simple answer.
Yes, if the information is provided to me, I'll be happy to analyse it.
Okay. Next one's from John Eamonson. Hi, Laurie. Thanks for the presentation. With hydrofoils becoming a more common occurrence these days, was there ever any thought of making the RiverCats dynamically supported, i.e. hydrofoils? Do you think that at operating speeds, the RiverCat hull would present less resistance than a similarly sized hydrofoil?
I think one would have to do some calculations to see that. I think Australia's expert on hydrofoils would be Martin Grimm. I think he might be listening tonight. You should contact him. I think he has shared some information with me in the past through email, indicating that hydrofoils produce a lower wave pattern than displacement vessels. So I think there's a case to be made for hydrofoils, but I think Martin Grimm is the expert on this topic.
He would be, yes.